Hey, welcome back. I'm Bradley. Today we're implementing a piano keyboard on this Blackboard FPGA. And excuse my one-handed operation, but the way that this works is that we're going to have a few inputs and an output, which is going to be this 3.5 mm headphone jack, which is going to act like a speaker. And how this works is that we're going to have a 16 input. That number of bits represent the number of notes in terms of the musical notes. I will be scrolling down in a little bit. We also have a hush. This acts as a mute button. So what I'm doing here right now is using the leftmost button to kind of control the hush. And since this is a button and not a regular switch, I have to hold on to this to keep the input on. If not, it would just resume the default frequency, which sounds like this. Of course, if this were to be programmed onto a switch instead, then I would not have to hold this down. And in this lab, we're going to be using decoder, an up counter, as well as the hush to mute the frequency coming out of the headphone jack. And the number of decimal places, the decimal sorry, I have to find a way to scroll up. Just give me 1 second. So according to this table here, we need to make sure that the highest rounded term of the counter is within the range of the bits. So since the highest number rounded count due to the half period clock cycle is going to be 113635, which means we will need to have our n to be 17 bits to be able to fit all of those decimals in there. And what I did was converted the decimal number into binary number for each of these 16 notes. And if you look at the left column, you're going to see the actual kind of like opcode, which means we're going to be using the most right for switches. So from switch 0 to 3. And each of these Ks is going to have a different frequency that represents the individual notes. For example, you have A4, and then for the code 0000, and then for 0001, you have A sharp or B. I'm not really into music much, so I may have messed up the notes, but so anyways, yeah, the main takeaway for this lab is just to complete the given code here. We had to code this part to make the hush, as well as the up counter decoder, as well as the 16 cases for the notes. And I'm gonna go ahead and get started on the demo right here real quick. So again, if I were to let go of that hush button, it would just keep on going like this. Could sound pretty annoying. So I'm gonna try my best to test this. So first case, 0, 0, we're gonna have the note A4, right? So desired frequency is at 440 hertz. And then if we were to flip on switch 0, we're gonna have the case for A sharp or BB. And I'm just gonna keep going so I don't have to glance back and forth. It's gonna waste a little bit of time, but we're now gonna test 0, 0, 1, 0. It's gonna sound like this. And then 0, 0, 1, 1. And then 0, 1, 0, 0. And after that, 0, 1, 0, 1. And then 0, 1, 1, 0. 0, 1, 1, 1. Now, all of these are going to be off except for the fourth most significant bit. So 1, 0, 0, 0. And then 1, 0, 0, 1. 1, 0, 1, 0. 1, 0, 1, 1. And 1, 1, 0, 0. 1, 1, 0, 1. 1, 1, 1, 0. And 1, 1, 1, 1 would be the last case. And again, it's a hush. Yeah, so for this lab, I learned how to put together the decoder case statements for the 16 notes, as well as using the up counter. And I would want to be able to continue in future labs to be able to make more hands-on experiments like this.